So, okay, thanks for coming. So I'm Fabien Albino. I did my PhD in France and now moved to Iceland at the Institute of Earth Science. And I'm a geophysicist and focus on the modeling of mechanical interaction between surface load change and magma storage zone, and especially in Iceland, in Icelandic volcanoes. Most of them are situated under thick ice cap. And ice cap evolves through times. We can have annual variation due to accumulation in winter and melting in summertime. And also ice cap retreat at long term due to the global warming. And both changes at the surface cause a load change. And from my numerical modeling, I quantify how the stress variation in the crust can affect the magma system of volcanoes. So we can define 3 different mechanics due to the ice cap unloading. It can influence the propagation of magma, the failure of a shallow reservoir, and also the production of the magma at deep level. And my research field, I focus only on the shallow part, on the failure of the reservoir. So, if I just move on, this is a sketch to illustrate my modeling. So, I have an elastic medium and consider as a homogeneous and isotropic. And I model the magma reservoir as an ellipsoid cavity. I apply at the surface an unloading event and calculate the stress change at around the magma reservoir. So one of the applications was in the Katla volcano, situated in South Iceland, under the Mýrdalsjökull ice cap. So Katla volcano is a subglacial caldera with a lot of phreatomagmatic eruption and glacial flows. And the last eruption was in 1918. And why this volcano in particularity? It's because we have very strong surface change for the Mýrdalsjökull ice cap. We have 2 different type of surface change according to the time scale. First, we have a seasonal effect with accumulation and melting of snow during 1 year. So you can have a difference of 6 meters of ice in the center of the ice cap. And you have also a long-term effect more at the periphery of the ice cap with a global decrease of thickness about 4 meters per year. And first, if we just focus on the seasonal load, it's interesting because if you look the eruption occurrence at Katla, you can see that all of the 9 last historical eruptions occur between May and November, and you have a gap of eruption from December to March, so during the winter period. And also in the earthquakes, you can see seasonality of the activity with a gap during the winter period. So do you have the key question that's can we have an interaction between seasonal load of the ice cap and eruption and seismicity? So I don't want to go to the detail in the mechanical principle, and just here I will give some results if I consider a seasonal unloading at Mýrdalsjökull. I have globally, I promote the failure of the magma chamber, means that initiation of magmatic intrusion will be enhanced during the snow melt period, and that consistent with the historical eruption. So just some conclusion I obtained during my PhD. It's that the surface load have an effect on shallow reservoir. It depends also on the shape of the magma reservoir and the load distribution at the surface. In case of Katla in South Iceland, the seasonal melting at Murdaljökull promote the failure. And I didn't go to this topic, but we can also take into account viscoelastic behavior when we model the long-term effect rather than elastic. Okay, thank you.
All right, thank you. So my name is Thomas. I'm a PhD student at Caltech. And so with the group, we're looking at the response of the Himalayan seismicity in Nepal to the monsoon. And the goal behind that is to try to understand better how earthquakes nucleate, how you start an earthquake when you put the fault under stress. So here is a cartoon that tries to explain how that works. So that's a cross-section of our field of study, so Nepal. Cross-section is like if you could take a nice slice of the Earth crust. That's what we believe you would see. So what you can see here is that's the Indian plate, and that's the Eurasian plate. That's the Tibetan Plateau, that's India, and Nepal is right here. And so those two plates are converging toward each other. So that one is moving that way, and that one is moving that way. And the boundary between the two is that fault. So MHT stands for Main Himalayan Thrust Fault. That's the main fault that we have under the mountains. And so that fault just slips during big earthquakes. The rest of the time it's locked. And so all the energy from the plate convergence is accumulating on that fault as a stress. And that's what those two small red arrows show here, the direction of the shear stress that you have on that fault. And because of all the stress that accumulates there, you have small earthquakes over there. And that's what we observe. So now how can the monsoon have an impact on that? So here is how it goes. So in the summer, the monsoon happens, it rains a lot, and all the water accumulates at the surface of the Indian plate. And actually the load of the water on the Indian plate is enough to bend slightly the Indian plate. So we can observe that with GPS stations that we've put in Nepal. I'm going to show later in time series. And what you see is all those GPS stations there that are north of where the monsoon accumulates move toward the south because of the bending. And now if you try to understand how that bending is going to have an impact on the stress, on the fault, so those are the two blue arrows that you have here. And a nice way to think about it is if you imagine you have a big book and you start bending it in the middle, the pages on the side are going to move like that with respect to each other, right? And so that's basically what happens here. That fault wants to move that way, so the top train in that direction and the bottom in that direction, if you bend the whole system like that. And so what you can see is the stress that you add up due to the monsoon here is opposite to what the tectonic loading stress is there. So you decrease the stress due to the monsoon here, and we observe less earthquakes. I'm going to show that later. In the winter, the opposite happens. So it's not raining anymore. The water has time to wash away, and so the plate unbends. The GPS stations move back to the north, and now the stress due to the unbending of the plate adds up with the tectonic loading stress, and you have more stress on the fault and then more earthquakes. So here is time series to show what I was saying. So the top one is, I just took a GPS station in Nepal, and that's the time series of that GPS station, and here's the seismicity rate. So it's the number of earthquakes in Nepal per month from 1995 to 2004. And so that just shows, again, what I was saying before. In the summer, so under the clouds here, the stations are moving to the south, and you see that usually you have less earthquake than in the winter after that. And in the winter, so that's the red rectangles, the stations are moving to the north, and you see that you have more earthquakes. And so what's interesting with that is that's a very rare way of stressing a fault, have that periodic loading. Because what you want to do if you want to understand how earthquakes work is you're going to create a model that says, let's say I put that stress on the fault. Is it going to nucleate an earthquake? Is it going to not nucleate earthquake? You want to understand that. So you create a model, and then you want to compare it with what you can observe. And in nature, you don't have that many examples. You have a fault that's just moving steadily. So you have a constant stress, and then you see the earthquake that happened there. The other stressing configuration that you can have on faults is the aftershocks. So you have a big fault that has a sudden earthquake. And so then the stress on all the neighboring fault changes suddenly, and all those faults react to that by creating their own small earthquakes, and that's the aftershock sequences. But that's basically it. That's what we have usually to test our models. Here we have a new configuration where you take a fault and you actually put a periodic stress on it and see that the seismicity actually responds to that, and that's a very good constraint for us. And actually in Nepal we're even more lucky than that, because we have two periodic loadings on the fault. So the first one is the one I was explaining, the seasonal variations here. So that's just the stress as a function of time. So you see that it's periodic, and the period is about a year. But you have another loading that's periodic. It's due to the earth tides. So the moon and the sun, we're more familiar with water and ocean tides, but they also deform the crust, and that creates stresses on the fault. And it turns out that in our case, those stresses are about the same amplitude for the tides as for what the monsoon does, but the period is really different. It's only half a day or 1 day, whereas here it's 1 year. And by the way, here we're talking about really, really tiny stress variations. The pressure that prevails where earthquakes happen is 500 megapascal, for those who are familiar with pressure units. So that means that here we have 3 kilopascal. We're about 100,000th of the stress that prevails here. And those small variations are apparently enough to trigger seismicity there. And so now if we take the stress due to tides and do the same exercise, look at how the seismicity responds to that, we are unable to see any correlation. And so those are two big constraints. The same stressing, same amplitude, different periods, that one doesn't trigger seismicity, and that one triggers seismicity. And so we can use that and then put to the test our nucleation models, the old ones that existed, and refine them and have more parameters. And one of the things that we can learn, for example, is the fact that nucleation of earthquakes is time dependent. It takes time when you put a stress on the fault to create an earthquake. So that we kind of knew before because of aftershocks. Because the way aftershocks work, you change the stress on all those faults, and then they create their own small earthquake days or months after the earthquakes. That means that they took time to create their earthquake. But here what's new and what we can learn is actually how long has that nucleation time to be. And here's how. The nucleation has to be longer than the Earth tides period, because the Earth tides period is half a day. If there is no correlation, what it means is that you start increasing the stress due to tides, and then the fault starts to want to nucleate an earthquake. But before it has time to actually create the whole earthquake, the stress is back down, and so the fault is back to square one and does it again, and so never really nucleate an earthquake due to tides. So we know that the characteristic time for earthquake nucleation has to be longer than half a day. On the other hand, we know it has to be short enough to respond to the seasonal variation of stress, which is a year. And so we know that the time of nucleation, at least in Nepal, has to be between half a day and a year. And that adds a lot of constraints on fault parameters and for our models. All right.
Good morning. Thanks for coming. My name is Shimon Wdowinski. I'm from the University of Miami. And I'll present a brief summary of our study with my colleague Igor Tsoukanov from Florida International University that shows that very wet tropical cyclones, and tropical cyclone is a generic name for both hurricanes and typhoons and cyclones. All of them are basically the same phenomena, but different part of the world, they call it differently. So the name is cyclone. Can trigger earthquakes, and so that's why it's called trigger disaster, because the cyclone itself is a disaster. There are a lot of flooding, then there are landslides, as we can see in the image here, and then the earthquakes come. By the way, there is copies of these presentations and a press release that issued by my university at the back of the room. So the motivation, we started looking into this issue because we noticed, especially last year, in 2010, there were 2 earthquakes that occurred within a short time after the same area. It's a tropical area that was hit by very severe wet cyclones. Last year, there was a Haiti earthquake that probably everybody remembers, with many fatalities that occurred in Haiti in a mountainous area, and it was 18 months after the same area was hit by a 4 tropical cyclones, actually 2 tropical storms and 2 hurricanes. And then a few months later, there was another earthquake in Taiwan, the Kwasing earthquake, a magnitude 6.4 that occurred 7 months after the same area was hit by very severe Typhoon Morakot, which had a record rain of 115 inches, which is a huge amount. It's about 5 times the average rain here in San Francisco that occurred in 5 days. So whatever we get here in 1 year, they had it in 1 day over there, over 5 days. And then searching, so that we found also that there was an earthquake in 1999, the Chichi earthquake that had a lot of devastation in Taiwan, and it occurred about 3 years after Typhoon Herb. Again, had huge rain. Occurred 3 years prior to the earthquake. Now, so this is the motivation. Now, in order to actually show that these relationships exist, went to look at the data set, and since Taiwan has both a lot of severe rain and wet typhoon over there, earthquakes, and very good data records, we looked systematically here in Taiwan. So this is the island of Taiwan, and what we can see over here, these are the location of the earthquakes. The one in green, the magnitude 5 to 6. The one in red, the magnitude 6 and up. And this is the record of these earthquakes in this region in the mountainous area. Now I can see a peak over here. The peak in around 2000, actually, this is aftershock activity following the Chichi earthquake. It was a large magnitude earthquake, 7.3. So we cannot use all of them. We need to actually remove the aftershocks that it won't bias our analysis. And here we see this is the record of the wettest typhoon in Taiwan. They are the 10 wettest typhoon according to the study of Lin and al. And we can see that there are 2 that are about 2 meters of rain, and one which is the Morakot that I mentioned was about 3 meters of rain, and we'll use that. So basically, we try to compare these 2 data sets and to see if we can see any relation between the 2. And here, this is the earthquake in green, and red, the occurrence of earthquakes, and the blue are the 3 wettest typhoon in Taiwan. And now we do a tracking to see how much it happened, what is the delay between. So this is, for example, this red over here. We calculated it's about 13 years, and we plot it here compared to the amount of maximum rain recorded by each of these events. And for example, here we see this is 3.2, and it's plots over here. And when we're looking at this figure, we can see that there is the red are clustered, located more red, which are magnitude 6 and above, are very close after the wet typhoon. With the green one, which are the magnitude 5 to 6, we cannot see any direct correlation. But then we resort to more statistics, and we did over here. So we put the same information here, but in histogram, in bars, as you can see over here. And you can see that the magnitude 6 and above occur mostly in the first 4 years. 85% of the earthquake occurred within the first 4 years. And we also calculated what is expected from what we call the background seismicity, what happens over the years. We calculated what is the background seismicity, and we can see that in the first 4 years, there is 85% of them, and it's 5 times as expected, more than expected by the background seismicity. We did the same analysis for the magnitude 5 and above, and we see again a higher amount of earthquakes right over here. But it's not as apparent here. It's only 35% of the earthquake occurred in the first 4 years after the very wet typhoon, and is twice as expected from the background seismicity, but it's still above the background level. Now, why these? I hope I convinced you that there are some relationship between this wet typhoon and the earthquakes that occurred right after the wet typhoon. The question is why, and this is what we suggest. The main engine that actually responsible for the earthquake is not the wet typhoon. The wet typhoon just determines the timing when the earthquake will actually occur. The main engine is the plate motion, the stresses that accumulate due to tectonic plate motion, and we call it tectonic loading. And that's horizontal as a plate move one with respect to the other, and they accumulate stress on these faults. These are the weak region in the crust that accumulate the stress, and eventually, after enough stress is accumulated, cannot hold it anymore, they rupture. Now, what happened is that the wet tropical cyclone, they impose or they pour a lot of rain, and it caused a rapid erosion. These arrows that show upward, it's not that they're moving up. Actually, it's moving. The erosion is going downstream, but basically we remove the load from the Earth's surface. So it's called unloading. The material is being washed to the ocean, and there is less. It's unloading, and as a result, there is a stress change over here at the hypocenter. And the earthquake can be triggered because there is unclamping the fault, there is less stress, and it's easier for the fault to move. And the geometry of the fault, the erosion over here, actually, due to the geometry of the fault line, is releasing the stress on that, and which enable the triggering or the rupture of the earthquake. Now, we did some numerical models. This is some area in Taiwan where there was this star is an earthquake. The line is where the fault, and we calculated using some kind of, it's called the Coulomb stress change, and calculated changes in the order after the hurricane of the order of 10 to the 3 or 1 kilopascal. I think it's related to what mentioned before. And such changes are small, but when they're added to the overall changes imposed by the tectonic plate motion, they actually encourage the occurrence of earthquakes. So to summarize, our motivation was that we identified 3 devastating earthquakes with magnitude 6 and above, and we then found additional earthquakes that occurred in tropical mountainous area shortly after the same area was subjected to heavy rain that imposed by very wet cyclone, whether typhoon or hurricanes. We used a systematic analysis of data from Taiwan. We looked at magnitude 5 and above earthquakes in the central mountainous area of Taiwan, and we compared it to the record of the wet typhoon from Taiwan. And we found that there is some relations between the occurrence of the earthquakes and the occurrence of the wet typhoon. 85% of the magnitude 6 and above occurred within the first 4 years after the wet typhoons, which is 5 times the expected, and 35% of the magnitude 5 and above also occurred in the first 4 years. In the model, we used mechanical models to calculate the stress changes after one of the earthquakes, and we saw that there is a small stress changes, but apparently big enough to promote the earthquake. Thank you.
monsoon patterns are expected to change with climate change. Can you speak to how those changes might affect seismicity in these areas?
The thing is, we're not really sure how they are supposed to change with climate change. Well, that would actually be good because we would have different, amplitude of stress if they changed. So now being predictive on what would happen, I don't think we're there yet. We might expect that with greater stress changes, we would have a larger variation of seismicity. But until we haven't observed it, it's hard to be really predictive on it.
I'm Alex Witzy with Science News. I have a related question for Fabien Albino. The reduction in the ice load since 1890 in Iceland, how much of that is linked to rising temperatures, and how do you expect that sort of long-term trend of less ice to continue?
So, your question is about the long-term effect in the future. I think so. Yeah, in Iceland, the Icecap retreat starts in 1890, and so we have a mean of 4 meter decrease each year, and it's still going on. And in the calculation we have also performed with viscoelastic behavior, and it seems that the effect is more than for a previous elastic we calculate. So we have a large effect on magma storage zone at shallow depth, and also on the magma production. I didn't tell a lot about, but you expect an increase of production of magma at deep level. So you have in the future you will have more magma at deep level to initiate some eruption if the magma go to the surface. So, and the process is still going on. We have some measurements.
This question is from Robert Zimmerman from BehindTheBlack.com. He's watching via web streaming. And the question is for both Fabien and Shimon. Are you suggesting these results can be extended beyond these particular locations? And if so, on what basis? And also for Fabien, what are the average magnitudes of the earthquakes produced by the Icecap loading?
So first of all, the magnitude of the earthquakes in the region is very small. It's around 2-3 of magnitude. We have a very seasonality in the pattern of earthquakes. And so for the application in other location, you ask?
Yes, the other question is for both of you.
Yeah.
Are you suggesting these results can be extended beyond these particular locations? And if so, on what basis?
Our results suggest that it can happen in other mountainous area in the tropics where it's seismically active. So other possible areas, not necessarily in the tropics, but areas that's subjected to cyclones. So such area can be Japan, the Philippines, maybe Central America. So that's something that we plan to explore in the future.
Yeah, so just for me, for other location, I am thinking. So in every location we can have volcano on the Icecap or ice, like in Kamchatka. But you also need a very strong. You need that the Icecap is very sensitive to the climate change and also to annual changes. So it's the case in Iceland, but I don't know exactly in Kamchatka.
Rick Lovett, freelance. This is a two-part question. First, how statistically significant are your correlations? The other part is policy. Can we use this for somehow or other reducing risk to life and property? Can this help us produce warnings or something like that?
Well, I think I presented in my study the statistical analysis that shows that at least the timing of the earthquake is above that expected. So we do take that into consideration.
What's the p-value?
The p-value for
how statistically strong, I mean, is it random?
Well, it's above, we use different statistics, so it depends what type of statistic you're using. According to what we show, it's above the background seismicity, way above that. And so if it depends what type of statistic you're using. But we did take that into consideration, so that's, and regarding the, about policies, I think it's too soon to say that, but I think in areas like Taiwan, that's something maybe that where we see the very strong correlations, that's something that they can maybe take into consideration, but it's very hard to take that forecast into policies.
Yeah, so in our case, we don't do a p-value. We do a test that's called the Schuster Test. It's a bit hard to explain. You take all the time at which the event happened. If you want to test if there is a year periodicity, you look at when in the year the earthquakes happen. And so then you take a 2D graph, and for each event, you do like a line of always the same length, and the direction depends on the time within the period where it happens. And so that way you make a walk. And what happens is if they happen all the time throughout the period, you're going to end up going back to the beginning. And if there is a periodicity, you're going to end up far from the origin. And then you can have the probability that you are that far from the origin. And so in our case, for the year period, the probability that what we observe is due only to random is 10 to the minus 14. So it's almost sure. There is another way you can do it. It's just like you take all your earthquakes, you stack them over 1 year, and you can try just to fit a sine wave. And then you can compare it to the standard deviation that you would have only through random process with the number of earthquakes you have. That's more just a comparison, but here again you have like way higher values. The probability would be of the same order of magnitude. Yeah. And then your second question was about the risk, how we can. Well, we can just tell them that we see more earthquakes in the winter than in the summer. There is not such a big effect so far on the magnitudes that we see, because all the magnitudes that we have are always in the same range. It's like 3 to 5. So it's just like the number of earthquakes that happen rather than so far what we have for the magnitude. So for the risk for people, there is no not big difference of just more earthquakes at that moment.
Hi, Stephanie from Live Science, and this question is for Shimon. Does the unloading from the typhoons, does it change the magnitude of the quakes versus what would have happened had the fault ruptured, without the influence of the storms?
Can you repeat the question?
So if you weren't having the storms, would the magnitudes of the quakes you'd expect to see on these faults, would they be any different than, the post-storm?
Yeah, eventually the earthquake will happen regardless if there was severe erosion or not, because the engine is the tectonic plate motion, and probably it would be the same magnitude. What the erosion or the unloading determine is the timing, when the earthquake occurs.
Harvey Lyford, freelance. I have a question I think it's for Professor Wdowinski. It's on the selection of the 4 years as the significant time period. How does that come about? It seems there are typhoons every year, more than one a year, and choosing 4 years comes from where, as opposed to 3 or 5 or 2?
In Taiwan, there are more than one typhoon a year. There's probably maybe 3 or 4. But what we're talking about, wet typhoons. So these doesn't happen every year. I mean, I showed the statistic of the 10 wettest typhoons. So the very wet typhoons I showed in this example over there, the 3 wettest, there may be every 15 over the past 50 years. There were 3 with a rainfall of about 2 meters and above. So it's roughly every 15 years, if you say on average. And we see that most of them happens within the earthquake that happens within a year or 4 years after the very wet typhoon. So it's not about any typhoon, it's a very wet typhoon that causes the erosion. Yeah, but then your background, the assumption about it's above, it will be greater. Yeah, you'll have all of them every 4 years, but what is expected will be also about 4 years. So you won't have this distinction between what you see and what is expected, because expected would be every 4 years. So there is no, you don't see any of this occurrence, concentration of occurrence right after a very wet typhoon. Now we did, there were some, the Marocot, which was the wettest typhoon with about 3 meters of rain, the one I mentioned. There were 2 earthquakes right after that, magnitude 6 and above, one after 3 months and one after 7 months, in 2 different locations, 2 different fault systems. And we did some statistics, assuming if it was a random process, what does it mean? And we got that if it was a random, if there wasn't any relation with that, to have such 2 earthquakes would be only it's less than 1% probabilities that will occur. And we see that concentration right after this very wet typhoon. So I think it's a good indication that it's related to that.
It's really a follow-up from this. It's a question directed at Shimon. Sorry, Steve Connor, The Independent. If I've got this right, what you're saying is not the typhoon itself that's triggering the earthquake, it's the soil erosion. Have you done any analysis of areas in the world where there are heavy cyclones but no soil erosion compared to areas where there's heavy cyclones and soil erosion? Now, for example, you've mentioned the Haiti earthquake of 2010. Haiti is renowned for being a heavily soil eroded place. I just wondered if you've done that sort of analysis or not.
I'm not sure I understand the question. If you can focus
okay.
it.
As I understand, your hypothesis is that it's not the cyclones triggering the earthquakes, it's the soil erosion.
That's right.
Have you done an analysis of places where there is soil erosion and places where there isn't soil erosion, but both affected by heavy cyclones?
It's very hard to find these locations. I mean, we start looking into that only after we notice these 3 devastating earthquakes. You need to have area that is subjected to, that is seismically active, is subjected to a lot of erosion, and then you start to look for such a relationship. And it's just the beginning of this type of research, and so far we identified Taiwan and Haiti, and the record is mostly from Taiwan, but we will look into that. So at the moment, I don't have any more information about that.
I'm sorry, this question is for Thomas, and it's from Robert Zimmerman from BehindTheBlack.com, and that is this a model or actual data at a specific location? And you may have already said that, but he missed it.
What is model and what is data? The earthquakes are data, just the number of earthquakes we have. The stress and the fault is a model, but it's used on data because we can observe the quantity of water we have on the Earth's surface. And so then if we have a satellite that measures gravity at the surface. So with that we know where the water is and how much there is. And then with that, if you have a good model of the Earth crust, which we do, you can compute the deformation and then the stress. And we have also all the stress and the deformations are really correlated tightly, and so we have all the GPS stations in Nepal, and so with that we can fit all the displacement over there. So we know that the deformation are well modeled, so that's why we think that the stress is well modeled, but it's like data that we convert with the model into more data.
And I have another question from Elisa Cheng from the Associated Press, and this is for Shimon. This is a follow-up from Rick's question. The U.S. Geological Survey's website says that large low-pressure systems with storms like typhoons and hurricanes are known to trigger fault slip, but it says the numbers are small and not statistically significant. Are you saying otherwise?
What people noticed before, and actually one of the meteorologists, this name very prominent meteorologist, suggested in 1924 that the low pressure of hurricane can promote earthquakes, and this is what we call dynamic triggering, that the changes occurs at the same time. When there are the hurricane or the typhoon is suggested because the 1923 Kanto earthquake, which destroyed Tokyo, basically occurred when there was a typhoon around there. So the low pressure of the typhoon can, according to that suggestion, can actually trigger earthquake. And it was found also a couple of years ago, there was a study by people that in Taiwan found that a slow earthquake can be triggered by the low pressure of the typhoon. Now, what we suggest is a different mechanism. It's not that it happened during when the typhoon is around, but there is a delay. And the delay of between 3 months and 3.5 years is due to the erosion. We suggest a different mechanism. It's not because of the low pressure system, but because of the erosion, the unloading. So it's a different mechanism and than suggested before.
Devin Powell from Science News. So both of these monsoon systems in Nepal and Taiwan seem to be looking at relatively similar stress changes. I think you said 3 kilopascals, you're looking at about 1 kilopascal. So my question is about the delay. Why are you guys looking at such different time scales then? It seems in Nepal you're looking at a seasonal less than a year delay, and in Taiwan you're going all the way out to 3 years. Is that because of a difference in mechanism, or why are the delays different?
What I can say about the Taiwan or the system that we studied, the delay can be due to different things, but one of them is that the unloading, the erosion, takes time until it's, the material is actually being washed to the ocean. So it's not a one-time event. I mean, you have the very wet typhoon that generate a lot of landslides. The material, some of it is being washed, and some of that can stay around and needs more rain in order to be washed to the ocean. Another thing is that you need to have more additional maybe tectonic forces to accumulate and actually promote it. So it helps, but the changes are pretty small and you need an additional loading in order to promote the earthquakes.
Great, thanks for your questions and thanks to our panelists.